Welcome to this short video that presents the Scikit-decide TSB for unified planning. Scikit-decide is an open source library that you can find on github.com that was initially developed by Airbus AI Research. It provides a catalog of domains and solvers, connected via a high-level algorithms from research and state-of-the-art algorithms to engineers, but also reversely to expose industrial problems and academic benchmarks to researchers across different fields of decision-making. The library offers domains and algorithms from reinforcement planning, scheduling, and planning. Thanks to its high-level interface, we can, for instance, define a planning domain and solve it using planning algorithms like A* or bindings to the unified planning libraries and solvers, but also using reinforcement planning solvers via bridges, for instance, to RLlib on the same problem. We specifically develop bridges from and to AI Plan for EU, thanks to UP Scikit-decide, and also thanks to specific hub domains and solvers linked to UP in Scikit-decide. With the first bridge, we can solve a UP problem using Scikit-decide solvers, and you can find them in the UP Scikit-decide GitHub repository. It starts with a UP problem that we embed inside the Scikit-decide UP domain that we then solve using a Scikit-decide solver, providing a Scikit-decide solution. All of this within the Scikit-decide ecosystem. And this Scikit-decide solution is then transformed back to a UP plan. So a UP user starts with a UP problem and see a UP plan at the end. But in between, it has been solved by using a Scikit-decide solver. In the reverse bridge, we want to solve a Scikit-decide domain defined as a PDDL-like semantic, but using UP solvers. And this is implemented in the Scikit-decide repositories that you can find here. We define a Scikit-decide domain that embeds a UP Scikit-decide problem that we then solve using a UP engine, producing a UP plan. All of this within the UP ecosystem. And then it gives back a Scikit-decide solution. So a Scikit-decide user will define a Scikit-decide domain and will, as output, see a Scikit-decide solution, but in between, we will have used the UP ecosystem to solve the problem. I will now demonstrate this with two different notebooks, one for each pipeline. So in this first notebook, we want to solve a UP problem with simulated action effects using Scikit-decide, and more specifically, the iterated width algorithm that allows to solve, let's say, planning problem using search and simulated action effects only. We start with some basic imports, and especially you can see here the UP-Scikit-decide module. For the problem definition, we just want to solve a very simple problem where we have a robot that can navigate between two different locations using a battery that will discharge when moving from one location to another. We define only one action, the move action here, whereas a robot can move from L1 to L2. And we can see here that we have this fun function that will discharge the battery whenever we move. We see here that the move action has a simulated effect, which is exactly simulated effect using the fun function on the battery charge of the robot. Now for the problem, we define two locations, L1, L2, run robot, and then we simply say that the robot is initially at the position L1, and the battery has a charge of 100, and we want to reach location L2, which will discharge the battery. Now to solve the problem, the funny part, we see that we first import the IW search algorithms from Scikit-decide. And then we just call the Scikit-decide solver from UP using the one-shot planner mode by giving two parameters. The first one is a solver that Scikit-decide will use, IW, and the second one the state features used by IW, which here are simply the state vector entries of the state. Then we solve the problem and return the plan. What we see here is that indeed UP is using the one-shot planner mode and the Scikit-decide solver backend. We see that it's indeed calling the IW solver, and here the problem is so simple that it has a width of 1, and only one action is needed to reach the goal, just in one step, with a cost of 1. Now I will show the reverse pipeline. More specifically, I will show that how we can use, in fact, UP to solve PBDL-like domains defined in Scikit-decide. So we start with some basic imports, and the most important one are here. So we see that we will use a UP domain class that allows us to make the bridge with UP problems from the Scikit-decide hub, and two different engines that we will use on our domain. The first one is lazy A star from Scikit-decide. The second one is UP solver, also from Scikit-decide, but which actually calls UP solver in the backend. Here, rollout is a utility function that allows us to roll out a plan and output some metrics and also actually the plan and the states that are visited. So we start with a basic example from UP that you can find on the Unified Planning documentation website. It's again about a robot moving between different locations, but this time without battery discharge. No simulation, no simulated action effects. Again, we want to move from L from to L2. That has to be connected. The robot is initially at L from, and the effect is to move the robot to L2. So we add our two fluents, robot add and connected, and our action move. Here we define some 10 locations, add those objects, and then say that we want to reach the last location. Finally, we also add some metric, which consists here in minimizing action cost. And since we have only one action, it's very simple. We want to minimize the only action cost of action move. Step 2 is to create the Scikit-decide UP domain that embeds our UP problem. You see that it's very simple. We call the UP domain class by giving it as input the UP problem. Here it's a domain factory, it's a lambda function that will be used by Scikit-decide. Step 3 is to solve the problem using Scikit-decide UP engine. So this is again a view from Scikit-decide users, right? So we first check that the domain is compatible with the UP solver, which is the case here because it's a deterministic planning domain. We define the UP solver by giving it two parameters. The first one is the operation mode, which is one-shot planner. And the second one is the actual UP engine that will be used, in this case, PeoplePlan. And finally, we say, we tell to the UP domain that we want to solve it with our solver by using the domain factory instance that we created here. Okay, and then we call the rollout function to have some nice outputs. Here we have some debug log that shows that the initial state here in PDL semantics and in UP, specifically semantics. And then we have the plan here, which consists in the successive move of the robots until reaching location L5. Okay. Sorry, location L9. Because here some output interleaves in between, but we see clearly that we reach the last position L9 in 10 steps. Now we want to solve a numeric example. So again, we model some UP problem. This time is different. It's with fluents X and Y, and we have three actions, A, B, and C. So we have our two fluents X and Y, our three actions A, B, and C. And initially, X and Y are false. The goal is to verify X. Again, we want to minimize some action costs. We have three different actions. Action A with cost 10, action B with cost 1, and action C with cost 1. Now we define the UP domain. The code is exactly the same as before. So we define a UP domain class and we give it the UP problem. Now to solve it, as simple as previously, we check that the domain is compatible with UP solver, which is the case since it's a deterministic planning domain. Even if the variables are continuous, that's fine for Scikit-decide. So now we create the UP solver using the one-shot planner operation mode, and this time calling the ENHSP optimal planner, and again doing some rollout. We see here that the plan consists in applying action B and C from the initial state. And we have some more outputs from here, UP ENHSP. What we want to show you now is that we can solve the exact same domain without redefining the domain, but just by changing the algorithm to lazy A*, which is a Scikit-decide algorithm. And it will allow us, actually, if we want, to compare two different engines from different communities, so from UP, or from Scikit-decide, and why not from reinforcement learning, which will be demonstrated in a later video. So here, you can notice that it's nearly the same code as before, but instead of calling the UP solver bridge, we simply call the lazy A* planner on our domain. This is exactly the same domain, and doing some rollout. Okay. No need to customize the domain or anything. And what we see is that again, we find the same plan consisting in action A, action B and C, sorry, exactly like with ENHSP, but using a totally different planner from Scikit-decide. That's it for today. Stay tuned for later videos demonstrating how we can use actually reinforcement learning on them. See you. Bye-bye.